Dr. Turner is the Rauner Distinguished Service Professor at the Catholic Institute for Cosmological Physics at the University of Chicago. His research focuses on the application of modern ideas in elementary particle theory to cosmology and astrophysics. We're delighted to have Dr. Turner with us here tonight, and we thank him for his assistance in making this program possible. So please join me in a warm welcome for Dr. Michael Turner.
Well, I thought it was going to be a little more intimate. I didn't think there were a lot of people who were interested in this topic. Good evening and welcome. Tonight's debate, as many of you know, is not the first debate on string theory. There have been many others, and to say the least, it's a topic that's attracted a lot of public attention. Most of these debates, I think, have generated more heat than light. And there have been strong, I mean, you won't believe this, but there have been some strong statements exchanged, like string theory is the theory of everything, or string theory is the theory of nothing, or string theory is not science, or those who do not embrace string theory will be left behind. And the only good thing about that last one is I don't think they're talking about the rapture. So I'm really pleased to be here tonight, and the three of us, this is going to be a debate, but I think we agree that we want more light than heat. And we particularly want to focus on the exciting science underlying the debate. In fact, I think the high level of interest in this topic has to do with the elephant in the room that often goes unnoticed. And that elephant is the fact that we are on the verge of a major revolution in our understanding of the universe and the laws that govern it. And that somehow sometimes gets lost, and we're going to make sure that doesn't get lost tonight. This revolution, some of us believe, I think all three of us believe, promises to be as profound and as exciting as the one launched by Einstein and others 100 years ago with quantum theory and relativity theory. And so I think what's underlying this, the elephant in the room, is the stakes are very, very high. String theory has not been bashful about its ambitions. Scientists are skeptics. And they can't really hear this, but I want to add, and have big egos to boot. Just a little more background here. Quantum theory has not only transformed the way we live by making the information age possible. I just want to remind you of that. Leon Letterman is fond of saying that 1/3 of the GDP is directly traceable to quantum mechanics. You laugh. The information, everybody agrees on the information age. The devices that generate the information, the devices that manipulate it, the devices that transmit it, all rely on quantum mechanics. And the Secretary of Energy has given me permission to turn off quantum mechanics for 5 minutes. Anyway, it's not only made the information age possible, but it has also enabled us to explore and understand the microscopic world with remarkable clarity and detail. And the culmination of this century-long adventure in probing inner space is, and particle physicists are rarely modest, is this modestly named Standard Model of Particle Physics. And, you want to describe it in one sentence, and I will. And it's a remarkable sentence. It provides a mathematical description of the particle world from quarks through atoms and molecules, and accounts for essentially all observed physical phenomena. On the other extreme, with general relativity, we have the standard hot Big Bang model. It provides a detailed and tested accounting of the universe from a fraction of a second after the bang, when the universe was just a hot, formless soup of particles, to 13.7 billion years later, when the universe is much more interesting. For example, we're here, stars, planets, galaxies, so on and so forth. There is no doubt in my mind that these two standard models are among the great intellectual achievements of the 20th century. And as scientists, what really gets us excited is not what they've done, but they've taken us to the next horizon where we can ask deeper questions about nature, and interestingly enough, discover that there is a crucial link between inner space and outer space, and that's going to be a big theme tonight. That all of a sudden the frontiers of studying the big and the frontiers of studying the small have merged. And so the stakes are much higher. It comes back to the high stakes for what we're doing here. And the questions we're asking now are, what is the origin of space, time, and the universe? What's the dark matter that we're certain is not atoms that holds together our galaxy and every other galaxy? What's the mysterious new form of energy that has repulsive gravity that's causing the universe to speed up? And by the way, that's causing it to speed up, what's the destiny going to be? Unifying the forces of nature and the particles of nature into a simpler framework. And last but not least, what we call the mother of all big questions. How are the twin towers of 20th century physics, general relativity and quantum mechanics, to be reconciled with one another? They're known to be inconsistent. So that's the backdrop. Those are the big stakes. And we believe that the answers are within reach. And again, string theory aspires to run the table. So that's what gets everyone's attention. And in debates, it's important to have simple, crisp propositions. String theory right along. And I think most of you appreciate that nature is far more nuanced. That we like to answer simple questions, and nature says, well, it's not really A or B. And so I doubt that even Brian would maintain that string theory as it stands today has the full truth. Nor would I think that his opponent, Lawrence, would argue that string theory has shed no light on these big questions. Before we begin, I want to add my thanks to the co-sponsor of this event tonight, the Office of Science at the Department of Energy. Not only did they help make this evening possible, but more importantly, together with NASA and NSF, they sponsored the research that's gotten us to this point. And they are sponsoring the research that is helping us answer these big questions. And if I could just say a couple words about the Office of Science, they play a special role here. The questions that we're asking require really big, sophisticated tools. In many cases, accelerators. And these accelerators allow us to build the most powerful microscopes, to look down to those scales, to recreate the conditions after the Big Bang. And DOE is exquisite at that. They run the Tevatron at Fermilab, which is the most powerful accelerator in the world. Most of you in this audience probably know that starting next year, there'll be a new accelerator. The mantle is going to be handed to CERN, the Large Hadron Collider. Many of you may not know that that accelerator would not be possible without the contributions made by DOE's Office of Science. The scientists played a major role in building that. And the Office of Science sees that we have really big questions here and is already making plans for the first global accelerator, the International Linear Collider. And so thank you, Office of Science, for all that you do. Now we're going to go on to the main event, and I want to introduce, let's see, I said this was going to be different, but I'll still call them the combatants, because we want to have a debate. I think you know them both, and they're great scientists and great communicators, so we're in for a real treat tonight. Brian Greene, we'll do it alphabetically, is a professor of physics and of mathematics at Columbia University. He's the co-director of Columbia's Institute for Strings, Cosmology, and Astroparticle Physics. That institute aims to apply superstring theory to cosmological questions, the linking of the big and the small. That's a big part of what we're going to be talking about tonight. Brian received his undergraduate degree from Harvard, and in spite of that, he's a really good scientist. And his doctorate from Oxford, where he was a Rhodes Scholar. I met Brian at the Roman Coliseum. I'm really glad he can't hear this. When he was a graduate student, and I was a young assistant professor, and he was most excited, apparently, about chatting with my girlfriend. But when that passed, he was already, as a graduate student, working on an extremely important problem. He was one of the first adopters of string theory. He was trying to calculate the masses of the elementary particles. So his greatness was already showing when he was a graduate student. He's now widely recognized for a number of groundbreaking discoveries in superstring theory, and he is known to the public and people in this audience through his lectures and writings. And I think we all know, this is a fact that I didn't know, that is stunning, The Elegant Universe, which was his first book, has, where did this say in my notes? I thought it had sold 1 million copies. Yeah. That's simply amazing. That's such a good book. His most recent book, The Fabric of the Cosmos, half a year on the New York Times bestseller list. And the local newspaper here, the Washington Post, called him the single best explainer of abstruse concepts, not pronunciator, but in the world. And so, Brian, can you join us? Now, Brian has a very worthy opponent in the same definite height and weight class. Lawrence Krauss is the Ambrose Swayze Professor of Physics and Director of the Center for Education and Research in Cosmology and Astrophysics at Case Western University. Lawrence received his PhD from MIT in 1982 and then joined the Society of Fellows at Harvard. As it turns out, I was a young assistant professor for a long time, so I met Lawrence when he was a graduate student. And again, he didn't try to shout at my girlfriend, but he it was between them and me, you know. He too started to shine as a graduate student. His thesis involved one of the most important problems. In fact, you wouldn't be here unless the problem eventually gets solved, is where did the atoms in the universe come from? Today, he's recognized as one of the leading cosmologists in the world, one of the pioneers of applying particle theory to cosmology. He's the author of 7 popular books, including the international bestseller, The Physics of Star Trek. Gosh, I wish I had written that one. And his newest book is Hiding in the Mirror, The Mysterious Allure of Extra Dimensions from Plato to String Theory and Beyond. Krauss has been described often as a public intellectual. And this last one I want to pause on because it's very serious and he's played a very important role here. He's led the effort by scientists to defend the teaching of real science in the public schools. When we agreed to do this, we really are very excited about the science, and we wanted to make sure there was more light than heat. We also wanted to have good fun, and we want this to be a scientific debate. And so earlier tonight, I've already told you my philosophy, and they said, well, gee, you know, they each like to have a minute on philosophy of this debate, so to make sure that they're both playing with the same rules. So, Lawrence.
Okay, well, I wanted to say that, in fact, this is a debate, and for some reason I spent a lot of time lately in debates, and I've debated a lot of intelligent design advocates, and I've debated people who have been abducted by aliens. But Brian, this is not really where you think it is. This is, I don't want to disappoint you all, but this is not that kind of debate. We were actually on the same side, and I want to make that clear up front. In a sense, we're scientists, and we like and respect each other, I think. And as scientists, we've worked on similar things over time. And so the debate isn't about, in my opinion, isn't about whether doing string theory is science or not. I don't think. It's a debate about the relative significance of events that have happened and the quality of the results that have come out. And so it's a debate among scientists. And in that sense, therefore, I view it as very different than the kind of debates that I've done in those other contexts. And that's really what I want to make clear.
Thank you. You may have already said in the introduction, we couldn't hear the back, but it's, I think it's exciting for both of us and gratifying that there is such an interest in these kinds of questions. I mean, I realized that when I got off the plane and I took a cab ride, and the cabbie didn't know at all who I was, and he just turns to me and asks me what I think about string theory. Pull up to red light, and there's couples yelling, "String theory's right, string theory's right." It's incredible. And that, again, is really the heart of what this is all about. But just to frame things slightly, I think Mike may have already mentioned it, but I mean, the ideas here are huge. I mean, in 1955, Albert Einstein was lying on his deathbed and asked for the pad of paper in which he had been scribbling equations in the hope that he'd find this unified theory that would put together gravity and quantum mechanics. I mean, he was so passionately driven, and even there at the very last moment, he was still trying to find it, and he didn't. And what's exciting to us in the field is that we may have that unified theory. We don't know, but we may have it in the context of this approach called string theory. And the one thing that I want to say at the outset, we'll come to what string theory is and all of that, no doubt, in due course, but I just want to emphasize that string theory fits right into the standard mold of the scientific method. However radical its ideas, it still fits into the mold of people come up with a germinative idea and they kick it around and they develop it, they try to extract predictions, and they try to test them. Now, string theory, as we'll discuss, does make predictions. The thing is that they're so far beyond what we can test with today's technology that it's hard to test the theory. So what do we have to do? But I just want to stress one point. However radical the ideas are, bear in mind that we are not trying to step outside the scientific method, which is something that has been out there in the press and in the media. We will not believe this theory until it's experimentally tested. So if you were to ask me, my final point, do I believe in string theory? My answer is no. Do I believe that string theory has incredible promise and is the best approach to unification? Absolutely.
Okay, I think that was a good...
I did break down about 10 times.
I've never succeeded in doing that with you before, so... Okay, I'm going to guide through a bunch of questions here, and I should have said, and we've reserved time at the end for questions from the audience. So, in the way of an opening statement and to get us rolling, I've asked Brian to describe what is string theory, what's its ambitions, and then we'll let Lawrence have his view on that. And if it needs some follow-up, I'll post them. So, what is it? What's its ambition?
So there are two main things that you should have in mind. First, the ambition of string theory, as we've mentioned now, is to put together the laws of gravity, general theory of relativity, together with the laws of quantum mechanics into one seamless whole. And the reason for that is there's some real realms in the universe, the Big Bang, the center of black holes, in which both of these pillars of 20th century physics need to be brought to bear, but as they're conventionally formulated, they are mutually contradictory. So we don't know how the universe began, we don't know what happens in the center of a black hole because of this conflict. That's its ambition, to solve that conflict. How does it try to do that? Well, let me just give you a gist of what the theory says. It rewrites the rules of what makes up the fundamental constituents of matter. We all know if you take that piece of wood making up the table, cut it in half, keep on cutting that piece into ever smaller pieces, you get molecules, you get atoms, atoms have electrons around the nucleus with neutrons and protons, you got quarks inside. That's where the conventional ideas stop. String theory comes along and suggests, and I underscore suggests, that there is at least one more layer to the story, that inside those particles there's something else. A little tiny filament of energy. It looks like a little piece of string. That's why we call it string theory. And these little filaments, these little strings can vibrate in different patterns. If it vibrates in one way, it would be an electron. If the string vibrates in a different pattern, it would be a quark. The notes, if you will, that the strings can play correspond to the particles of nature. That's the basic idea. Now, it turns out, and this I won't try to answer now, I presume we'll come to it, this little change from the old picture of a dot to the new picture of a filament winds up resolving the conflict between general relativity and quantum mechanics. That's why we're excited about it. We have to go further and see whether it describes other features of the world. That's what we're vigorously pursuing.
Great, that was concise.
Yeah.
Good. My ambition.
Yeah,
So what's your take on what string theory is and its ambitions?
I have one slide. It's probably enough, but it's actually got words. So the first person says the other I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. The other one said, okay, what would that imply? First one goes, I don't know. So that's my take. I think, as we'll talk about, there are fascinating reasons, and I've written about them in my books about for why people were driven to string theory, interested in string theory, and it was and it has been fascinating to think about. The point that I want to make is that it really hasn't lived up to its promise. In fact, as a Nobel laureate Frank Wilczek says, string theory is promising and promising and promising and promising. And it's been around for 37 years, and I know, because Brian and I talked about it, I was going to say that's a short time in maybe the history of science, and it is, except it hasn't really explained any of the things that it originally we hoped it would explain. It, in fact, has gotten less and less clear as time goes on what the theory even is. It's in some sense more complex and diffuse. And it less and less clear, I think, what the ultimate predictions, if it ever can or will make them, are. And I hope, and I think part of the reason is something that Brian alluded to in a way, that one of the things we want to celebrate here tonight, and I really do want to celebrate, is that particle physics is a real field. It's not just philosophy. It really involves amazing discoveries, and we've learned a tremendous amount in the last 40 years. I don't think people even appreciate how incredible the change in our understanding of the fundamental structure of the universe has been in the last 40 years, and we should celebrate that. But that has come from this remarkable interplay of experiment and theory working closely together. And it's not just people inventing things in offices and chuckling and drinking beer, and it really is that interplay has been very, very important, and that interplay has been missing in string theory. Now that doesn't mean it's wrong, but I think it means that it's worrisome because most ideas in physics are wrong. That's what makes it hard. And it's not so surprising to have really great ideas that don't work out. And it's not at all clear that in spite of and we'll probably get to some of the interesting reasons why people think about string theory, and Brian's alluded to one, but it's not at all clear that it really has anything to do with nature. And in fact, I'd say after 37 years, it's less and less clear that it has anything to do with nature.
Let me, the next question, we've segued into it rather nicely. And I want to sharpen the issue that Lawrence raised here about where's the beat, what has it done. And I'm going to give you each a chance to sharpen it. So I'm going to ask Brian's next question, and because Lawrence needs a little extra time, I'll give him his next question. Brian's next question are, what are the triumphs? So Lawrence has said, 37 years, haven't done anything. So what do you view as the triumphs? And then you'll come back and what are the failures? Because theories do more.
Yeah.
And that's not a unique feature. And there are snippers along the way. We see signs. Yeah. And so what do you Brian, try to be as specific as possible here in terms of why is it excuse me. Why is it? What are the signs that you see, and why is it that there are a large number of people involved in this activity? What are the successes? And try to be very specific.
Number one, string theory puts together general relativity and quantum mechanics into a mathematically consistent framework for the first time in the history of physics. Number two, this framework that unifies the big and the small winds up embracing almost all of the most pivotal ideas in the history of particle physics in the most natural way. It could have been that this theory puts together the big and the small, but you look at it and it manifestly has no relation to anything that came before. Instead, this theory embraces the ideas that those of you who are familiar with these things in particle physics will know about. Gauge symmetry, the powerful approach to describing the particles of matter. The theory naturally organizes the particles into the families, the categories that experimenters have found throughout the years. It naturally has a way to give particles mass. The so-called Higgs mechanism finds a natural home within string theory, the way in which we can protect certain things, like making protons stable so the world doesn't disappear, as a natural incarnation within string theory. So this way of embracing the past and looking to the future at the same time, to me, is the most compelling reason for believing in the theory. Number 3, the theory has given us insight into the nature of black holes. In the early 1970s, Stephen Hawking was able to finesse some of the difficulties in putting gravity and quantum mechanics together to predict that black holes have something called entropy. It's an idea that no doubt many of you are familiar with. They embody a certain kind of disorder, but he was unable to pinpoint microscopically where that disorder resided. String theory comes along, studies black holes, is able to pinpoint the origin of this entropy and calculates a number for the amount of entropy, and it exactly agrees with what Hawking found in the 1970s. These are the reasons why many of us feel that this theory is going in the right direction. I'll finish by noting why is it so difficult to test this theory. You know, Lawrence was alluding to that fact. Briefly, the strings we envision are pretty damn small. How would you test it? Naturally, you'd sort of make a powerful microscope and you look down and you say, there it is, the string. And we can't do that. We can't come anywhere near doing that because in the conventional approach to this theory, the strings, and perhaps I'll come back to this, are about 1 billion times smaller than the distances we can probe with even our most powerful accelerators. That makes it hard to test the theory. The theory gives rise to a notion of extra dimensions that maybe we'll come to, but these extra dimensions are so small that we can't probe them. If we had a machine that was sufficiently powerful to probe these tiny distances, we wouldn't be having this debate. Either the theory would have shown the extra dimensions, the experiments would have shown the extra dimensions, or they wouldn't. So this is the issue.
So Brian has pointed to successes. Do you want to point to some failures?
Well,
you want to
that would take too long, I think.
No, I just want to make one thing clear. I have in my back pocket yellow cards and red cards. Those of you that are not familiar with
Okay.
soccer, 2 yellow cards equals a red card. So what about the failures?
Well, no, let me put in context. I think Brian was being a little disingenuous. String theory doesn't predict anything about the number of families that there are, doesn't say why there's an electron, doesn't say why there are 3 families, doesn't say why the electron mass is so light. All of the key questions that we don't understand. It doesn't say why there's matter and not antimatter. It doesn't answer any of those questions. It's all plausible within the context of string theory, but it doesn't by any means even predict that the electron exists. It's a possibility. In fact, in new versions of string theory, which some people in string theory will talk about, are promoting, anything is possible. Literally anything is possible. And that we'll come to that question of whether that's science. But I think one of the great thing about the string theory is that every time it has a failure, it's proclaimed to be a success. And it's important to realize that string theory predicts the world has at least 10 dimensions. Why? Not because of anything fundamental we measure about the world or something that drives us in that direction. It predicts that because the theory doesn't make sense unless there's 10 dimensions.
So Lawrence, do you have some evidence that there aren't 10 dimensions?
No, but I think it's important. It's an important difference. It's that, but it doesn't explain why the world. I mean, you look fairly three-dimensional, sometimes two-dimensional, I mean, we don't experience. One of the things you'd hope a theory that would describe the world would naturally explain why we happen to not see those extra dimensions. That's a real problem in string theory. It always has been, and it sort of doesn't naturally come out. It doesn't say why you can't have 8 dimensions getting wrapped up in just a 2-dimensional universe left over. That's I think something that string theorists themselves have recognized as an issue. One would also have to say that some of the things that are proclaimed successes are. By the way, you didn't mention. My mind, one of the most interesting things about string theory is that there's a very interesting symmetry of nature called supersymmetry, which a lot of us think may really exist, even if strings don't. And we're going to look for that in the next generation of accelerators. In actual fact, to be fair, the first realization that might be an interesting symmetry of nature came from the very early mathematical formulation of string theory back in the days when we didn't know if it had anything to do with gravity. And so I think that's one of the interesting things that, in some sense, has come out of string theory, the realization that there could be this interesting symmetry of nature. So I want to point, that's a success that I think is important. But hold on.
Okay.
But let me just say the black hole thing is part of what I do as one of the big failures. No, wait. String theory is purported to be a great unification of gravity and quantum mechanics. But there are two questions that I, even as a graduate student, were pressing questions that I want to know. When black holes evaporate, if they evaporate like Stephen Hawking said they do, what happens to the information in black holes? Now, string theory says something of black holes, but not black holes in 4 dimensions. Not regular kind of evaporating black holes, very special kinds of black holes of higher dimensions. And we don't know if, in fact, when you make the extrapolation to 4 dimensions, any of that will carry on. It is true that there's an interesting calculation, a number in 5 dimensions that would agree with what you get from Stephen Hawking, but it doesn't tell me anything about how black holes evaporate or how the information loss paradox is overcome. And the other thing, which we'll get to, the one thing you think that the theory of quantum gravity should tell us about is the energy of empty space. And that's been one of the greatest discoveries, most remarkable discoveries made in cosmology in the last 20 years. And string theory failed miserably to predict it, to understand it, and to explain it, except in a way which I'm not sure Brian or I would find palatable. Maybe you do. We'll talk about it. But so those are some of what I would say are concerns.
Let me ask Brian a hard question here, and it'll segue into this some broad things that I think those of us who are involved in theory take as good signs that you're on the right track, that you're putting a quarter in the machine and a couple of bucks is coming out. But Lawrence has raised the point, and I want to ask the question directly so people hear the answer. So can you point to a number that's been measured somewhere, or something, a number of generations, or any number that string theory predicts and an experiment has measured so far?
No, I mean, I was very clear in that in my open remark that we've not yet tested. That would be a tested theory. So if you want me to reemphasize that point, I'm happy to.
No,
just to be real clear, we've not yet been able to test this theory. And the reason is because of the scales involved. And let me just go back to Lawrence's criticism, just to lay out a little bit, it'll take me a moment with the science behind it. Lawrence is pointing out that, which is true, we've not yet predicted that there should be an electron with the properties that the electron is measured to have. And the reason for that is the properties of an electron within string theory are determined by the exact geometry, the size and shape of these extra dimensions that we've been alluding to. And the problem is we don't know what the extra dimensions in string theory look like. There are many, many, many possibilities. This is a real problem for us because every different form of the extra dimensions gives rise to different detailed features of the world around us. This is what research is about. There are open questions that we are working very hard to resolve. The point that I was making is that the general structure of the theory does give rise to particles in groupings that are akin to the groupings that we see in nature. It didn't have to happen that way. It could have been that the particles were scattered and didn't resemble any kind of groupings that the measurements actually reveal.
You say they have to be?
Oh, absolutely. Yeah.
You can't have a universe that's different. You can't have I think I don't know whether it should be questions.
Let's go on. I want to come back to this. I don't want to get into technical details here. But what I do want to get to, I think everybody here has said it, that the hallmark of physics is that we're not creating worlds that might have been. We're trying to find out how our world really is. And so there's a sense of there's a good time to explore a certain idea. For example, when I was a graduate student, there were people working to unify gravity and quantum mechanics, and they were just so far from any kind of testability that it was a small group of people, that's fine, but it wasn't a major activity. And so I think that let's turn next to, are there experiments? We get this LHC that's going to be turned on. After that, if you want to allude to the ILC, I think you'll Light Ray and others up here.
Answer last question, but you skipped the
answer a lot.
Didn't theory falsifiable that you gave Brian, but you got to get the same.
I don't know. We did successes and failures. Let's now talk about how are we going to test this theory. We've got the LHC coming up next year. We've got you pick any experiment, the Joint Dark Energy Mission, microwave background. If you want to go to the ILC, so are there some signs that could maybe give us a number or could say we really are on the right track?
Yeah, I think the answer to that question is yes, but I'm going to cede my time to my colleague in a sense of fairness. I would like to just mention a few experiments, and part of this will amplify Lawrence's point, so in some sense,
I don't have this for you as well.
Okay, exactly. There is no way that we can make the kind of definite predictions that if they aren't found, the theory will be proved wrong. That's something that we can't do. We can't prove the theory wrong in any of the other experiments. That's a real issue. That's a real
burning bush.
But we can possibly show that the theory is right, or at least show that features of the theory, as you say, are going along the right direction.
That's two different things. We can't show the theory is right. The second part.
No.
Okay. You said that.
Well, let's hear about the burning bush.
Okay. So.
I think. Yeah.
Okay. So there are experiments that are going to be taking place, as we've heard, at the Large Hadron Collider, this big atom smasher accelerator in Geneva, Switzerland. And that machine may find these supersymmetric particles that Lawrence was alluding to. That wouldn't prove string theory. That would prove the supersymmetric quality that does happen in other theories. But you might also actually see the vibrational resonances of the strings themselves. You pluck a violin, and you know that the string vibrates in various patterns, and it has overtones associated with the patterns. That's what gives the music its richness. The same thing happens with strings. They can vibrate in various patterns and various overtones, which are multiples of the wavelengths of the primary vibrational mode. And there's actually a chance in the modern way of thinking about string theory that the data will show evidence of those vibrational modes, the tower of vibrations. That will be pretty convincing indirect. We can't see the strings, but that would be an indirect signature of them. What else might happen? You may produce microscopic black holes. This is, again, one of the natural things to emerge from string theory. If you produce them, it doesn't prove the theory right, but, when this points to it, and this points to it, and this points, all the spokes on the bicycle wheel are pointing in one direction, you begin to have confidence that you're going in the right direction. Final thing I'll mention is not with an accelerator, but with astronomical observations. So something I'm working on is to look at the heat left over from the Big Bang, the so-called cosmic microwave background radiation, because our calculations suggest a possibility, not a definite, but a possibility that strings may have left an imprint on that. Let me give you 1 minute of how it goes, and then we'll move on. If I had a little balloon here, and I had a really fine tip pen, and I scribbled a little message on it so small that you can't see it, you can see it's there, but as I blow air into the balloon, the surface stretches, and my little message gets smeared out across the surface of the balloon, making it much easier to see. That may have happened in the universe. The young universe is really tiny, strings are really small, they may have left an impression on the young universe that we can calculate. Too small to be seen, no one there to see it anyway. 14 billion years of cosmic expansion takes place, and the impression of string theory gets smeared out across the sky in a way that we may be able to detect. And again, our calculations suggest that the way you would detect it is really tiny temperature variations in this heat left over from the Big Bang. So again, if you literally see the tower of vibrational modes, that to me is pretty convincing. If you don't see those, but you see all these other features, it begins to make you really feel you're going in the right direction.
So Lawrence, it sounds like Brian has pointed out possible signs, not a proof, but signs that string theory is on the right path. Agree? Disagree?
Obviously, I disagree, but and I think.
So if all those things happened, you wouldn't be any closer.
No, hold on. There certainly. We both agree that supersymmetry is discovered. It's certainly an interesting, in my mind, if supersymmetry is discovered, well, it's probably the most likely direction we're going in. It's by no means a proof that string theory is right, but it is.
I call a little time out here.
Supersymmetry is
Define,
okay.
Define supersymmetry.
I don't know if
what the
help,
sign would be.
but all the particles in nature form two different types, depending on how they spin. They're quantum mechanical spin. There's particles called bosons and particles called fermions, and they're very different in behavior. And supersymmetry is this remarkable symmetry of nature that relates those two. And as a result, you can do lots of things, and probably we don't have time to go into the kind of things you can do. But it's one of the reasons it might help us understand why the scales in physics are the way they are, why the weak scale is where we can measure it, why gravity is where we can't measure it. So that's an interesting symmetry, and there's a lot of reason to believe in it. It's totally independent of string theory. If that's discovered, it'll indicate that one component of it is in the right direction. By the way, if supersymmetry isn't discovered, it doesn't mean string theory is wrong, unless, of course, the resolution of these problems is discovered at the Large Hadron Collider or at the ILC, and it's discovered to be totally different than we think, which is always possible, and from a theorist's point of view, the most exciting thing. We want experiments to discover something we hadn't imagined at all, because that's usually what happens, in fact. And that's why we're guided by experiment and not by theorists.
But what about these other examples?
Okay,
The black hole
but
and the
the problem is,
so if a black hole came out of a collision at the LHC,
it would tell you,
would say...
Well, the interesting thing is that prediction did not come out of string theory, per se. It came out of people thinking about the possibility that there are extra dimensions and they're large, and the idea of extra dimensions was motivated by string theory, but it proposed a scale is vastly different than the string theorists originally imagined. And it might be true, but it's not by any means a string theory prediction. It's a prediction that gravity is much stronger than you would have imagined naively, which is an interesting prediction, and it has to do with the problem in particle physics that's largely independent of string theory and one that isn't even resolved in string theory, the hierarchy problem. But the thing that we're all getting in this trap, this linguistic trap, and I think, unfortunately, Brian has led to it, that string theory isn't a theory. It isn't a theory. It doesn't make predictions. It's a hope for a theory. We don't even know whether the strings are the fundamental components of the ultimate theory. In fact, there's good evidence that they're probably not, that there may be membranes that there's whole components of the theory that people are just trying to understand. So I don't think it's even fair to say it's a theory. It doesn't make predictions, as Richard Feynman says, it usually makes excuses. It really tries to, instead of saying, here's something I'll make a prediction and we'll test it, what it does is it says, well, we know what the world is like, and we're going to try and modify our theory until it matches the world. Well, that's interesting, but I don't think that's very impressive. It's actually very disappointing, and I think, frankly, the standards are a little lower than they are in string theory than they are in the rest of particle physics, where you actually have to explain something. And another example that's been used, and I'm trying to provoke Brian because I know. But I think that when one talks about the successes, someone said that string theory is like a new form of archery. You shoot the arrow, and then you draw a bullseye wherever the arrow lands. And I think, that's pretty cool.
Let me
I don't want to see any parts of it.
I want to move in a slightly different direction here, and I want to change the order. I'm really just curious.
No. Look, if I saw a lot of extra resonances, it would certainly be really clear evidence that something like string theory or collusive line theory, for example, from 1917 might be right.
So you do agree, though?
It means that there's neat new physics that's associated with extra dimensions.
Being really grudging here, Lawrence.
Hold on. If in 1926 we discovered them, what would you have said?
We discovered what?
All these extra resonances. You would have said this great theory called collusive line theory that was invented, which no one talked about because there was no evidence for it. And back then, you actually had to have evidence. but you would have said, hey, that's the evidence of collusive line theory.
Okay, I think Brian asked a very clear question.
No, but it was certainly, to be fair to you, it would certainly give it that the directions that string theory is moving in are clearly the right directions if you saw it.
Okay, so the record will indicate yes.
Yeah. So you do agree that there is a possibility that these ideas
are right. Oh, sure. No, there's absolutely a possibility. I see there's no reason to believe it now, but there's a possibility they're right, and there's a possibility lots of things like that.
Right, I know, but if you went into Antonio Stradivarius' workshop and picked up a block of wood and started to play it and said, Jesus doesn't sound very good, It'd be a natural explanation that it was a work in progress and it hadn't developed to the point where it actually could produce the music that you were wishing it would.
Oh boy,
so within a few years, there's really a chance. I mean, I consider it a long shot, but I just want to, in principle, chance that these ideas really will be on the table.
I think I want to go in a slightly different direction here, because the one thing that we all loudly agree on is that this is a special time in science, that we feel like the solutions to really big problems are within reach. And Brian is here telling us that string theory is going to give us guidance that might be the right answer. And we know that in science that, sometimes ideas are not fully correct, and sometimes they're dead wrong. But ideas are important to guide, that science is not, and I know you wouldn't be saying this, but science is not just a list of random facts.
Yeah, sure.
It's understanding. So theory is really important. Although the facts are important to verify the theory, it isn't just we go out and measure a bunch of stuff. So what are the alternatives? I think the next question we'll be able to talk about is, let's turn the tables. And so what other guidance are we getting? Here we are on the verge of a major revolution in understanding of space and time and how the universe was born. So what are the alternatives? What are the other ideas that are guiding us? And how are they doing, by the way? Is there some other idea out there that's got 15 pluses?
Well, no, the point is, if there were, we wouldn't be having this discussion, right? I mean, we would, we would be, extolling the virtues of this great new discovery that actually did something. Instead, we're talking about a fascinating idea that hasn't yet done anything, but that's fair. It's a fascinating idea. But
we're talking about a league here.
Some people said
string theory is not very good, but it's in first place. Is that right?
Yeah, but it's important. But I think it's important to realize that that's often been the case in science. And then the real theory comes along and gets the answer right. In fact, it's happened to string theory once before. String theory was developed as a theory of a strong interaction. When accelerators were first discovering a lot of new particles in the 1960s, there were hosts of new particles coming on, and it looked like there were an infinite number of them. And the theory just was so complicated, no one ever figured you'd have a way around it. And in fact, strings were developed to try and explain that. And it turned out that they didn't. That in fact, a much simpler idea that recently won the Nobel Prize, that protons are made of quarks, and these quarks have a really interesting property, that the interactions between them get weaker as they get closer. And it explained all of that stuff. And so at the time, string theory, or a version of string theory, was really for late 60s, was the only game in town. And it was in many ways, just as mathematically attractive, almost as mathematically attractive as now. It just wasn't right. And so the fact that it may be, and it is, I think, mathematically the most intoxicating set of ideas around for many young people. But that doesn't mean it has anything to do with reality.
So let me lower the standard here a little bit. One funny thing that theorists love to say is that sometimes a wrong theory is more important than a right theory.
But what do you mean by wrong?
I'm asking the question. Okay. So in science, sometimes an idea, a wrong idea, can push people to think in new directions, can frame things. And I'm just wondering, because you've been given the side to speak out against string theory, what do you think? Has it helped in this quest to try to unify the forces and try to understand? Has it at least provided a straw man and a framework to push people in certain directions, to make measurements, to make progress, even if it doesn't turn out to be correct?
Well, to try and be balanced. The basic
fair
answer,
balance.
it's fair and balanced in a non-Fox News sense. But the short answer, of course, is no. But let me just. There is one area that I think string theory, on the whole, in fact, that's what's disappointed me most about string theory, is that it hasn't done precisely that. 25 years ago, I thought it would have given some direction to people to look at things, to make measurements that they wouldn't have made otherwise, or to push us into new directions. And it just hasn't done that. In fact,
So the short answer is no.
No, but the one area that I think it has, to be fair, is it's caused people to think about what might be possible if there are lots of extra dimensions. And that's been an interesting area of theory. And I think that also, it's caused people to realize something that the string theorists didn't argue, but that may be even more fascinating, that these extra dimensions aren't tiny. They're actually big. They're infinite. There may be infinitely big extra dimensions that we can't see. And what's amazing is that they're not ruled out by experiment, and maybe the next generation of accelerators might be able to detect them. And I think that's a fascinating idea. I think it's probably wrong, frankly. But I think it's a fascinating possibility, and I have to say it wouldn't have come up were it not for string theory. But that's the only area that I can think it's given any direction. And in fact, the key great discoveries in cosmology is given the wrong direction in my mind.
Brian, you've been sitting patiently here. So you can talk about other theories, or this question is, has string theory, because you said it's a work in progress, has it pushed people, has it provided a framework, has it provided a challenge? Sometimes if you've got a theory out there, someone will go out and do an experiment that they wouldn't otherwise have done. Someone will build a big accelerator, or somebody, if you want to respond to that, Lawrence says we gave up a grudging one, but you want to take a...
I would say there definitely are examples of that. I mean, the calculational methods that string theorists have developed have guided people doing more traditional calculations in particle physics, allowing them to complete calculations that they absolutely would never have been able to complete otherwise. So these are calculations in quantum thermodynamics that string theory guided those calculations earlier on. Now, subsequently, after people get the insight from string theory, they found various ways of reframing it without string theory. But you're asking me, has string theory pushed in other areas in a positive direction?
Pushed experimenters to do something?
No, not experimenters. Again, an experimenter has to come to my office and say, what should I look for? And I can't give anything sufficiently specific that they would go out and build a machine to look for. The changes in the temperature fluctuations in CMB, people would look for anyway, because this is a fantastic way of probing the early universe. We are making predictions about what they may find, but they would be doing that experiment anyway. It's a deep and important experiment to undertake. Another link, though, to ongoing experiments is the stuff happening at Brookhaven. The RIC experiment, relativistic heavy ion collider. I don't know how many people are familiar with it, but this is a machine that is basically taking gold atoms, not protons, but heavier objects, gold atoms, and slamming them together at very, very high energies, recreating high temperatures unseen since just a moment after the Big Bang. And what's particularly interesting is string theory has given calculational methods that have allowed scientists to at least gain some insight into this plasma, this early universe-like plasma that comes from these collisions. It isn't saying that string theory is right, but it is a link to experimental undertakings that string theory is helping to flesh out. Let me just finish just by going back for half a second, because I really don't want to leave a wrong impression. And this is not in the spirit of rebuttal, but I really think you give a slightly wrong impression. When you said that string theorists keep modifying the theory so that it comes closer to reality, I trust you would agree, string theorists are really guided by rigorous mathematics, and they're led by the mathematics. And the mathematics is really what dictates where we go. It's not as though one pulls something out of left field, pulls something out of right field, which I think may be the impression that gives.
Yeah,
let me finish, and then if you want to respond to it, please do. There is, tens of thousands of pages of rigorous mathematical calculation behind string theory. I don't want you to get the sense that it's somehow some floppy theory that you can come and massage in any way to try to make it look like the real world. It is a rigid, highly constrained mathematical undertaking, and every previous attempt to put together gravity and quantum mechanics in a consistent framework has died by virtue of the math not making sense. This is a very hard nut to crack. Any theory that's able to put together the laws of the small and big in one consistent mathematical framework is hugely attractive and highly constrained. So it's not as though one can just keep moving the theory around and hope that it hits something close to the real world.
Two things. One, I don't want to give the impression that string theory isn't valid mathematics or that people are pulling things out of their pockets. But remember that. It's not, at the same time, string theory, for example, the mathematical rigor doesn't predict 4 large dimensions. When you actually talk about compactification, it's not something that's so that you have 4 large dimensions of 3 dimensions of space and 1 of time that we live in. That doesn't come out of the theory. The thinkers say, well, I've got to figure out how in my theory I can finagle things so that 6 of these dimensions, if there are 10 of them, disappear and are invisible, and the 4 we see are large. And that's driven not by the theory, but trying to make it agree with the world. If it came out of the theory naturally, I'd be jumping up and down, but I'm not. And
but along those lines, I should point out, my own work, which is trying to establish that, this is what research is about. Came within a hair's breadth of that result. And it turned out that so far we were unable to get that result. But yes, that's an open question that becomes so close to address.
But that's what I mean by the fact that theory, you have to mold the theory because you say, well, I know there are 4 large dimensions.
No, not molding the theory. I don't know if you've read these papers, but we really tried to do a cosmology.
But they didn't do it.
That's right. I agree with you that we've not yet gotten there. But to me, it was impressive that it was so close to being able to get there that I think with future work, again, that's what research is. You don't always get the answer within a month or a year.
That's the problem with string theory. It keeps not being able to do things. And we keep hoping it'll do things, and it doesn't. Now, the one example you gave, in fact, I'm proud of one of my students, as you know, did the calculation. But it's a pretty modern, after all of the tens of thousands of human years, you're figuring 1,000 bright young people working for 30 years. So yeah, we've been able to improve some calculations of the strong interactions, which some people in strong interaction business say they could do anyway. And that's true. And therefore, string theory has had a use, but boy, it's a really modest success after all of that time. It's just,
but I'm saying this is not the time to judge the theory because we are trying to answer, which in my opinion, I think you probably agree, the most difficult, the most profound question in the history of science. If we haven't gotten to it by whatever number of years you say, 37, if we haven't gotten there in 50 or 100, as long as we're making progress, as long as we are understanding the theory better, I think that's a pursuit that we should be
But I don't want it to answer the most profound question. I just want it to answer one question.
No, but it's a tactic deal, man. You go to the shop and you want to buy a car and it all comes together. We can't answer piecemeal.
Let me
this is really important. One of the most stunning features about string theory is, and the way in which I would say it slightly deviates from science in the past. Science in the past was divide and conquer. You answer this little piece of physics, you answer this little piece of physics to do with particles, to do with cosmology, and little pieces stick together and build a puzzle of the universe. One of the things of string theory is it doesn't have a divide and conquer element to it. It's either right or wrong in the sense it's trying to answer the big questions. And that is both dangerous and potentially spectacular. If you want to take a risk, you work on it and hope that it will turn out to spectacular, but it's absolutely a risk. That's what science is about.
This is a really good segue.
I think it is.
I want to sort of summarize this section from what I ambitious. It's a work in progress. And what I would want to say is that we don't have any better ideas right now.
Well, I don't know.
Yeah, and so let me
see back to the purpose of moving on.
I want to move on to one sociological question. We'll see how that goes, and if it doesn't go well, I want to move back into some crystal ball gazing and experiments. But I think even people in the public, and certainly people who are in academia, know that there are big debates about, do departments have too many string theorists? Physics departments. Is it unhealthy for the department?
Let you go on and go to finish this. I'm going to answer differently than you might imagine. I'm not one of the people who immediately says, hey, this should be worked on. It's unhealthy for people.
So it's not physics.
Hold on. I think there are some concerns I want to raise, but I firmly believe that students should work on whatever interests them, and physicists should work on whatever interests them. They have to be driven by their curiosity. And I applaud the goals that young people who are going to string theory or lots of other things are aiming to try and answer. They should be encouraged. In fact, physics is only healthy when there are lots of different avenues being looked at. And some people have been concerned that string theory has been promoted so aggressively that so many young people are going into it that in particle theory that other avenues may not be explored adequately. But the point is, I don't think students should be told to do. They got to do what excites them, because the only reason to do this is because you find it exciting and fascinating. And so, as Brian knows, some of my students have gone on to become relatively well-known string theorists. But, and I wouldn't want my daughter to marry one, but still. So I think it's important. I mean, I think it's ridiculous to say this shouldn't be being done, but I think it is really important to realize that physics is best when there's a happy balance. And I think that's what some people are expressing concern of, that there hasn't been maybe a happy balance. And maybe the reason there haven't been other avenues as explored as well as string theory is that we just haven't been funding or encouraging students or young faculty who aren't working on string theory to be able to do that. The other concern I do have is that because string theory is so mathematical, and I've seen this happen, especially there are a set of young people who have been grown up with this and think of the mere little questions like why the electron is 2,000 times lighter than the proton, or why there are 3 generations. That's not interesting to them. Their view of physics is not what my view would be, and I think that I'm a little worried that there are some of them, and not a lot, because I actually think the minute the next collider discovers something exciting, you're going to see a lot of the rats jump to thinking shit, because you're going to see a lot of people working on string theory are going to move to something else when there's something else exciting to do. But there still is going to be a lost part of that generation, I think, is lost, who really don't know the difference between mathematics and physics. And I've met some of them, and not as if they're everyone, but there are some of them. And you probably have to agree.
So let's see, you're saying that your view on this is the Chicago school, market forces, and so you should let the best and the brightest do what they want to do. And right now, many of the best and the brightest are doing string theory, and you personally don't agree, but...
No, I mean, as I said, I've taught my students to do what interests them. But yeah, I think best and brightest, but it's important to realize that some of the best and brightest who aren't doing string theory should also be encouraged to do what they're doing. Brian?
Yeah, I mean, who could just agree with that. But, I do think it's important to recognize that, in the marketplace of ideas, the fact that so many students want to work on string theory, these are hungry students who, I have to tell you, in my experience, are the most critically minded scientists that I've met. I mean, when I tell my students some aspect of string theory or physics in general, I always get a response from them. They always want to push back in order to find a flaw or to find a hole in it. I mean, it's not as though I'm a professor on high to these students and somehow what I say is dogma. I mean, every so often I frankly wish it was, to make life a little easier at times. But that's the way the marketplace of ideas works. I have students that work on string theory, I have students that don't work on string theory. In fact, right now, the majority of my students are working on problems at the interface of string theory and cosmology that, 5 years ago would not be really thought of as studies in string theory per se. And that's true of also the faculty that we're bringing in. We're bringing faculty that are really straddling the divide. And it's not jumping ship. It's just that we see that new data is coming in from WMAP, satellite experiments. New data will be coming in from Planck. And we need people who can look at that data and talk to us who are well-versed in these ideas of string theory and fundamental physics. We also bring in faculty who are at the edge of particle physics and string theory beyond the standard model type undertakings, because again, new data will come in from the Large Hadron Collider, and it's not that we'll be jumping ship, it's enormously exciting to have new information that can try to incorporate into these ideas.
I want to follow that up. I mean, I think it's true that students are critical, but I think at the same time, the reason Brian and I both went into particle physics is because it seemed to us the sexiest thing around, asking the most fundamental questions about nature. And students get sucked in, and we can go there later. But so I think some of the students get drawn to it because of their impression, because there's been so much, because they're led to that. I don't want to use the word hype, but they've been led. They believe that's the case, and so it's natural. If you're a young student and you think that this is going to unify everything, it's kind of natural to be drawn in there. But it's important. I think it's important for us to give students also problems that they can actually address. That's the first thing. But the second thing is, you really implicitly mentioned it, and I think it's true, and you have to be honest. string theory has been in the doldrums for the last 5 or 10 years, and that's why you're seeing more and more students doing other things and more young faculty doing other things. It's just not been good times for string theory.
So you're saying market forces?
Yeah, are market maybe not jumping the ship, but they'll be in more natural balance unless there's some new developments. I think you'll tend to see. Unless there's some new developments in string theory, I think you'll tend to see more people getting frustrated and maybe trying to find other areas where they can answer questions.
So I think I agree.
Again, I have to keep one of your responses. Only partially, really, because I agree that string theory has been fortunate to have periods of incredible activity that we give the name revolution. It's the understated way of describing what's happening in the field. 1984 was what we call the first superstring revolution, where the math of string theory for the first time was shown to really work. 1995 we call the second superstring revolution, because there we were able to refine the mathematics to analyze the equations with a precision that nobody thought we would ever be able to do. And I was a graduate student. I never thought that we'd be able to do the kind of precision calculations that we are now able to do within string theory. And indeed, we haven't had that kind of intense flurry of activity that we would label a revolution, but the progress has been sure and steady. So doldrums, no, I wouldn't say that at all. It hasn't been a revolutionary time, but the progress has been impressive.
Let's not. We talked about successes and failures, but let's move on, because I think we have a consensus here that there's no widespread conspiracy that's only installing string theorists. That we've got market forces in the U.S. and right now, for whatever reason, maybe it's good salesmanship or maybe it's the best idea in town, people are attracted to this idea. I want to.
Do they exist? Can we detect them? Are they real?
It doesn't matter.
Doesn't matter. And indeed, when you think about gravity, from the point of view of Einstein, you don't see gravitons. You have this curved space idea. A ball rolling around on a warped trampoline is the metaphor we often use. So where are the gravitons? The gravitons come in when you put quantum mechanics into the story. So when you put quantum mechanics and gravity together, you find that gravity, like any field, has a fundamental packet, a smallest unit, and for gravity it's called the graviton. The electron is the smallest unit of the electron field. The photon is the smallest unit of the electromagnetic field. Apply gravity, quantum mechanics to gravity, you find the graviton is the smallest unit of the gravitational field. We have not detected gravitons, and the reason is because gravity is a fantastically weak force. I don't know if we've actually said that explicitly in the discussion tonight. Maybe we did. But it's a force that is perhaps 10 to the minus 39 times, say, as strong as the electromagnetic force. It depends exactly how you define that difference, but that's the kind of smallness of this weakness of this force that we're talking about. Gravity is so weak, if you try to look for the smallest packet of the weakest force, that's a challenge. And that's why no one has found these particles. But if, indeed, gravity and quantum mechanics go together, it would be gravitons. And if string theory is correct, the graviton would just be a vibrational mode of the string.
Let me expand. Can I expand on this for a second? Let's go on to another question. This is not a debate. This is information. This is what they came for.
But we got a lot of questions.
Okay, anyway, the bottom line, you'll agree to this, is that we've seen the classical version. We've seen gravitational waves. And we know that those exist, that in gravity, one of the great predictions of Einstein's general relativity is that if you shake a mass in a certain way, it emits gravitational waves, just like if you shake an electron, it emits electromagnetic waves. And those we've seen, or indirectly. We haven't seen them directly, but in fact the Nobel Prize was given for the fact that when an amazing phenomenon, when you get these two very heavy objects, the neutron stars orbiting around each other, they emit gravitational waves, and their orbits change in such a way you can calculate with general relativity. The calculation agreed incredibly accurately with the observations. And so we know gravitational waves exist, and that's remarkable. And gravitons are just the quantum version of those.
In the middle back there.
Explain with string theory, trying to bring together a lot of different ideas of gravitation and quantum mechanics. Is it possible that looking at it as strings may not be the thing, but the mathematics is in the right direction? Putting the mathematics and strings together, maybe there's another way of looking at the mathematics.
Yeah, so the answer to that question, did everybody hear?
No, I don't think they did.
Yeah, so the question is, a lot of mathematics has been developed in the context, in the framework of string theory, trying to put together gravity and quantum mechanics. The question is, could it be that the math is somehow right and heading in a given direction that might ultimately require we discard this initial idea of strings and just follow where the math leads? And the answer to that question is absolutely possibly yes. We are, in my view, in the infancy of this deep, rich theory. And historically, we got there by thinking about these vibrating filaments and developed the math to understand how they move and how they interact. As we've gone forward, we've realized that the theory actually has other ingredients applied to these little strings. It has membranes that we call brain for short, extended objects. And it could well be that when the final version of this theory is written, the strings might not be the primary element, might not be the critical element. It could be that they are a stepping stone toward the deep understanding. And historically, if that book is written 100 years from now, it might say this wonderful idea of string theory came along, and it turned out to guide scientists toward the true understanding of the unified theory, but it was just a guidepost. It wasn't the actual core idea. That's absolutely possible.
I actually expand upon that. I think it's likely. In the sense, if you look at the evidence of theory right now, that with the realization, this is the amazing thing about this second revolution in string theory in 1995. In 1984, the big statement was we had almost a theory of everything. This is string revolution that put everything together. It looked like we're on the verge of explaining everything. Then 10 years later, 11 years later, the second string revolution came along. What did it tell us? That theory of everything was missing an infinite number of things. That really, that these brains are vitally important in the theory, and maybe much more fundamental, in fact. And so it amazes me. It should give you some historical perspective that this theory had almost everything, was missing a tremendous amount at the time. It was really a premature statement. It's likely that those statements now are premature for the same reason. But all the evidence, if you look at the realization of brains and maybe an 11-dimensional theory and M theory, is that strings may just be some effective thing if the theory is right. Just like particles were thought to be an effective thing in string theory.
Let's take a question from this side. Sir.
Does string theory have any implications for the creation of the universe? For example, what we see?
I'm going to try to get one answer per question so we can do more questions.
I think, although I thought from the audience, I missed it. Well, I think Brian should have a chance to answer this.
I liked it a lot better when they were both graduate students.
The answer is yes, of course. Well, the question was, could string theory have any implications for understanding the Big Bang or what happened before the Big Bang, if there was a before? And in fact, many people think that time began at the Big Bang, so the question isn't a good one. And the answer is obviously yes, because if it's a theory of quantum gravity, the real reason that Mike and I and now Brian do cosmology as well as particle physics is that the macro universe, and I didn't hear your introduction, so you may have said this, that because the universe is expanding, it was once much smaller, and at the very earliest moments, in order to understand the structure of the universe today, we have to understand the fundamental forces on the very smallest scales. And there's this beautiful uniformity between physics, so that the physics at the very large scale and the very small scale get tied together at the beginning. And that's what makes it so exciting, and that's what made me, as a particle physicist, go into cosmology, because the universe is a laboratory for particle physics. But, so the answer is, if it was a theory of quantum gravity and to understand quantum gravity on very small scales, the very beginning of the Big Bang, the entire universe exists at a very small scale, obviously would have implications. However, if you ask the question, has it had implications, the answer, in my opinion, is no. And that's what's been another big failure. It really hasn't given us any insight into cosmology that I know. There have been lots of ideas, but they haven't led to any. There have been tons of ideas and tons of papers. And again, I don't criticize the people working on it, because maybe one of them is right. But right now, it hasn't had any insight that we didn't have, in my opinion, just from good old standard general relativity.
Sir, this is a question about dark energy, and it's near and dear to my heart.
What do you think? No, I don't think Why don't you take this?
So the question was, could dark energy have anything to do with extra dimensions? And Lawrence got it right. This is the biggest mystery in all of science. We've given it a name. We don't really have a clue about it, and so why not?
Well, my speculation was maybe there's not as many stars being created anymore. So that the person who posed the question or posed the postulation that some experts believe that we heard on this line.
Well, it's getting older. Sure. And what the evidence? I mean, the evidence is that, in fact, I just gave a lecture yesterday at London on this, that the future is miserable. But the universe.
Was that referring to tonight?
That this amazing discovery that the universe, the expansion of the universe, is accelerating. If that goes on forever, it tells us that the universe is going to get cold and dark and largely empty. All the galaxies outside of our own cluster of galaxies will eventually be moving away from us faster than the speed of light, and they'll disappear, and the universe will become dark and empty and cold. And if that's what you mean by the decline,
that's the closest thing to a real astronomer here. I think there's an easier question. The one thing that astronomers can now measure is the star formation rate. And we're over the hump on that. Most of the stars have been formed. Stars live a finite amount of time. We can say with great certainty in 1 trillion years there will be no more stars.
No, 10 trillion, I think.